In this lesson, we will introduce another concept, and that is the concept of a frame pointer. And so a thing to keep in mind is that during execution of a module, we might need to move the stack pointer, but that can be difficult and for a number of reasons. First of all items in the stack frame are based on the stack pointer, and it provides for a useful context for other elements that require offsets to be based off of it. So it's providing a fixed position for various registers that are appropriate for our current procedures. So in order to maintain our stack pointer, we introduce an appropriate register that has a fixed point in reference to the current procedure, and this is going to be our frame pointer. So the frame pointer allows for us to make use of the stack frame and utilize a specific entity that can keep track of appropriate elements as our procedure advances. And so this is just a general purpose register, and it'll contain the address of a known point within our activation record for our functions. And so this point of reference wouldn't change during execution of our procedure. And so why exactly do we need a frame pointer? Well, to illustrate, let's take a look at an example method. In this method, foo, we have a number of different variables that are declared. We have our integer p, which is the parameter that is passed into the method. We also have variables a, b, as well as an array called c. And the size of the array c is the value that p is. So the end of it would be p minus 1. We have our assignment that cp minus 1, the last element in the array is going to be equal to b plus a. So now let's take a look at how our frame pointer would handle the execution of this procedure. So let's take a look at our stack. Here we have our stack pointer that contains our local variables, and then we have our frame pointer that is pointing to the address of the previous frame pointer. So let's try to figure out what happens as our procedure executes. So we have our frame pointer pointing at the previous frame, and then we have our local variables which hold our stack pointer. So how is our procedure stored in this depiction of our stack? For our local variables, we have a and b, which are pushed onto the stack. And so the location of a is going to be the stack pointer plus 1. To put that in perspective, the location of b is going to be the stack pointer. Our stack pointer is going to point directly at b. And that is because it was the last element to be executed after a. As we progress through our procedure, we come to int our declaration for c of p. And so from here on, we have element c, which is allocated for the size p. And our stack pointer will point to the first location of our array c. And so still at this point, we still have that a is at stack pointer plus 1, and B is that stack pointer plus 0. And so now with the addition of our array of C, A is now going to be the stack pointer plus P, which is the size of the array that has been declared, plus an additional 1. On the other hand, B is now going to be located at the stack pointer plus P, since it will be right after the declaration of our array C. So now what we have is B is incremented. And so this B is still located at our stack pointer plus 0. As we popped C off of the stack. So B is now incremented, and then A is also incremented, and A is at the stack pointer plus 1. And so we'll take a look at Foo's stack frame and we'll make a revision to it. In this case, what we're looking to do is we're going to add a frame pointer register. And this will point to this is where our frame pointer is going to refer to. And so now let's take a look at things in perspective of the inclusion of our frame pointer in respect to the stack pointer. So with respect to our local variables that we have, now we have that B is located at our frame pointer, and it is frame pointer minus 3. As we continue to execute through the program, through the function, B is still at frame pointer minus 3. And then as the program continues to execute, it stays static. So this does not provide for a change in where B is being referenced at on the stack, because we're doing it in regards to where it's located on the frame, with regards to the frame pointer. So now let's consider what happens after the callee stores our previous frame pointer and it copies the contents of the stack pointer into the frame pointer. The callee is able to save the frame pointer on the stack, and this in turn sets the frame pointer to the stack pointer. The next step, the callee is able to save the registers S, and then those values are what are used during the execution on the stack. And so our stack pointer now is incremented, and we push our local variables onto the stack. And this is done by the callee in order to allocate appropriate space. Okay, next, before our return, the callee needs to restore the previous S registers from the stack. And so now our stack pointer still points to local variables. Our saved S registers are being restored. This in turn results in us popping our local variables and our saved registers from the stack. And now our stack pointer and frame pointer both point to the previous frame pointer. And so as we continue to execute, we have our jump, which results in no change to the stack. And so now that we have completed our procedure, the stack pointer points to the previous return address and the frame pointer is no longer needed. Our caller will then need to restore the previous return address to its appropriate register. We'll then have the caller will then need to store the additional return values if they are needed. Those are then popped off the stack. The caller will then move the stack pointer to remove the additional parameters that have been previously stored upon procedure execution. Now this in turn results to the caller restoring the previous T registers from the stack. And so this allows for us to make some software implied modifications to how we're able to utilize the stack to incorporate appropriate ways to reference components on the stack with regards to a given procedure or function. So it's important to keep in mind that this type of offset with respect to the stack pointer can be a problem area for compiler writers. And so the frame pointer is incorporated so that we're able to utilize the stack efficiently for the given procedure with an appropriate reference point for local variables. And so these are some appropriate considerations that we need to keep in mind with regards to utilizing the frame pointer. As a software convention, the frame pointer allows us to utilize the stack with a reference point that is appropriate to our procedure or subroutine that is currently executed. And this provides us with a concrete perspective for a specific frame of reference on top of the stack.
Hey everyone, and welcome to this Python and OpenCV course. In this course, we'll be
And so utilizing the frame pointer provides for a way for compilers to more easily make use of the stack without changing values that might be needed later. This means that the variables will always have the same distance from the frame pointer that doesn't change. And so with this in mind, what is the most important thing that we need to remember as to why we need to keep track of a frame pointer? Is it because it's faster to access a variable through the frame pointer than it is to access it through the stack pointer? Is it a waste of our our registers? Is it something that has always been done, and so we're just keeping it that way? Or does it provide us with a single, consistent, and constant way to reference local variables in a stack frame? And so with that in mind, you do want to keep in mind that it does provide for us a consistent way to reference variables that are needed for a specific sub-procedure or subroutine with regards to our stack frame. So there are some additional considerations that you want to take into account when we're working with multiple routines and subroutines, or procedures and sub-procedures. And so let's say we have our method main and we have our method foo, and we assert that foo does not use S registers. It uses T registers. We have our method bar. Bar makes use of S registers, and it uses T registers too. It also has appropriately local variables. We have the method baz, which does not use S registers, and it has no local variables. It'll accept one parameter, and it also returns one value. And so with both of these, with all three of these, we have different considerations to keep in mind. So let's consider how these would function on our stack frame. And so let's take a look at our activation stack for our baz method. It does not make use of our S registers. It doesn't have any local variables. It accepts one parameter, but it doesn't have any additional return values. It also does not have any additional parameters to consider. And so let's put this into perspective with regards to all three methods. And so this puts things into perspective with regards to how all three methods would utilize it. And so with consideration to our method baz, we have our frame pointer pointing to our previous frame, and then we have our return address registers as well as our T registers. And so when we consider the stack for bar, we have our T registers, we have our return address registers, we have our previous frame pointer, and we have our S registers. And then at the top of this frame is our local variables. So this puts things into perspective of some of the considerations that we need to take into account when we are utilizing a frame pointer with subroutine calls that have various frames that need to be considered with regards to the stack.